When 135,000 pounds of tractive effort meets an 80-pound piece of cast steel, the steel doesn't bend. It shatters, like a fragmentation grenade. The big boy could pull harder than any locomotive ever built. That's what made it legendary. That's also what made it a killer. But because the machine designed to haul the heaviest trains in America kept tearing those trains apart. Not occasionally, routinely. And when a coupler snapped under Big Boy's power, the catastrophe that followed killed the men working between the cars. This is the story of the engineering problem Union Pacific couldn't solve. The deadly physics of slack action. And the brakemen who paid the price when American horsepower exceeded the limits of American metallurgy. The Janney automatic coupler, the hook-and-knuckle design used on every American freight car since the 1890s, was rated for 150,000 to 200,000 pounds of pulling force. That seemed adequate. Most steam locomotives of the 1930s produced tractive effort in the 50,000 to 80,000 pound range. Even with slack run-in, the violent jerking that occurred when a train's couplers slammed together after stretching apart. The forces rarely approached the coupler's breaking point. Then Big Boy arrived with 135,000 pounds of starting tractive effort. More than double what conventional locomotives produced. Yes, and when you coupled that power to a 100-car freight train weighing 6,000 tons, the mathematics of destruction became inevitable. The problem wasn't steady pulling. Big Boy could haul its rated tonnage all day without breaking couplers, as long as the train stayed stretched tight. The problem was starting. Stopping. Grade changes. Anywhere the slack between cars ran in or out, because a freight train wasn't a rigid object. It was 100 separate cars connected by couplers with 3 to 6 inches of slack in each coupling. Total slack in a 100-car train, 25 to 50 feet of play. Odd when a Big Boy started a heavy train, it didn't pull all 100 cars simultaneously. It pulled the first car. That car pulled the second. The second pulled the third. A wave of tension rippled back through the train as each coupling took up its slack and transmitted force to the next car. If the engineer applied power too quickly, the slack ran out violently. Couplers slammed together with enough force to lift fully loaded freight cars off the rails. And sometimes, more often than Union Pacific wanted to admit, the coupler at the point of maximum stress simply broke. And the first recorded Big Boy coupler failure occurred in March 1942, less than 6 months after the locomotives entered service. A westbound freight departing Cheyenne for Sherman Hill. Engineer applied power to start the 110-car train. Normal throttle setting, standard procedure. The train began to move. Then 40 cars back, a coupler shattered. The break was instantaneous. The knuckle, the curved hook that interlocked with the coupling on the next car, fractured across its narrowest point. Metallurgical analysis later showed the steel had failed in tension. Pulled apart by force exceeding 180,000 pounds, well above the coupler's rated strength, the kind of force only Big Boy could generate. When the coupler broke, 3 things happened simultaneously. First, the pneumatic brake line connecting the cars severed. Air pressure in the brake system dropped instantly, triggering emergency brakes on the rear section of the train. 70 cars went into emergency braking while the locomotive and front 40 cars continued accelerating. Second, the drawbar slack that had been stretched tight under Big Boy's pulling force suddenly released. The rear section, now braking hard, has decelerated rapidly. The front section, still under power, accelerated. The gap between them widened at combined speed approaching 20 miles per hour. A third, and most deadly, the brakeman positioned on the train to monitor coupling operations was standing between the cars when the separation occurred. He had seconds to react, jump clear, or be crushed when the brake application slammed the rear cars forward while the front section pulled away. Yet he didn't make it. Found between the cars, cause of death, massive trauma from crushing between couplers during slack action. Union Pacific's accident report classified it as operator error. The engineer had applied too much power. The brakeman hadn't maintained proper clearance. Or the coupler was defective. None of these conclusions addressed the fundamental problem. Big Boy produced more force than standard freight car couplings could safely handle. The second incident occurred 2 months later. Same route, different crew, same result. Coupler failure 50 cars back. Brake line severed. Emergency application. Slack action crushed a brakeman working the train. This time, Union Pacific's mechanical department couldn't blame operator error. 2 identical failures in 2 months suggested systematic problem. Tests were conducted. As engineers measured coupler strength across the freight car fleet, they found what they expected. Couplers rated for 150,000 to 200,000 pounds nominal capacity. But nominal capacity assumed steady pull. Add dynamic loading from slack action, the sudden shock when stretched couplers slammed back together, and the effective strength dropped significantly. Some couplers tested well below 150,000 pounds before failure. Big Boy's 135,000-pound tractive effort was within the nominal rating. But add slack action multiplier, typically 1.5 to 2 times the steady-state force, and you got peak forces approaching 200,000 to 270,000 pounds. Well into the failure range for older couplers. And Big Boys were pulling the oldest, heaviest freight cars in the fleet, the ones most likely to have worn or marginal couplers. Yet Union Pacific issued new operating rules. Engineers operating Big Boys were instructed to apply power gradually when starting heavy trains. Stretch the slack slowly. Avoid sudden throttle movements. Let each car take up load gently before adding more power. In theory, this prevented the violent slack run-in that generated peak forces. In practice, it didn't work, because Sherman Hill grades didn't allow gentle starts. A Big Boy hauling 4,000 tons up a 1.55% grade needed power. Lots of it. Immediately. You couldn't ease into it. Either the locomotive pulled hard enough to overcome rolling resistance plus grade resistance, or the train stalled. And a stalled train on Sherman Hill required helper engines to restart it. Expensive. Time-consuming. Operationally unacceptable. So engineers did what they'd always done. Opened the throttle and pulled. And couplers kept braking. The third incident killed 2 men. June 1943. Eastbound freight descending Sherman Hill toward Cheyenne. A Big Boy running in dynamic braking, using the locomotive's weight and traction to hold back the train's momentum on the downgrade. Standard practice. The engineer maintained speed at 25 miles per hour, safe for the curves and grade. Then a coupler failed. Not from pulling this time, from pushing. If the locomotive was holding back the train, the freight cars behind were pushing against the locomotive's resistance. Compression instead of tension. The coupler, weakened by previous loading cycles, failed in compression. The knuckle broke. When the coupling separated, the rear 80 cars lost their restraint. They were descending a 1.55% grade at 25 miles per hour with nothing holding them back. The emergency brake application triggered by the broken air line wasn't enough. 80 loaded freight cars, 4,800 tons, accelerating down a mountain grade. The train reached 50 miles per hour before derailing on a curve 2 miles from the separation point. 37 cars destroyed. 2 brakemen riding the train killed in the derailment. Union Pacific's response was immediate and inadequate. The railroad ordered inspection of all couplers on cars assigned to Big Boy service. Just replace any showing wear or cracking. Install only the highest-rated couplers, 200,000-pound minimum tensile strength. This helped, marginally. Coupler failures decreased but didn't stop. Because the real problem wasn't coupler quality, it was physics. So Big Boy generated forces at the upper limit of what Janney couplers could handle. Any variance, worn coupler, sudden throttle change, unexpected grade transition, pushed forces into the failure range. And freight operations involved constant variance. You couldn't control it. You could only accept it and count the casualties. Between 1942 and 1945, Big Boys operating over Sherman Hill experienced 23 documented coupler failures, resulting in train separations. 8 of these resulted in crew injuries. 4 were fatal. Union Pacific didn't publicize the numbers, and accident reports attributed most incidents to defective equipment or operator error. But the mechanical department knew. and the crews knew. Big Boy was dangerous to the trains it pulled. The problem extended beyond Union Pacific. Norfolk and Western, all which operated massive 882 compound mallets producing over 150,000 pounds of tractive effort, experienced similar issues. So did Chesapeake and Ohio with its 2666 Alleghenies. Any locomotive generating tractive effort approaching or exceeding 135,000 pounds stressed couplers beyond their reliable operating range. And the solution, if you could call it that, was operational adaptation. Railroads using high-power locomotives developed procedures to minimize coupler stress. Graduated power application. Limited throttle when starting on grades. Distributed power, placing helper locomotives mid-train or at the rear to spread pulling forces across multiple points instead of concentrating them at the head end. These measures reduced failures but imposed operational costs. Slower starts. Helper locomotives. Reduced train lengths. And the ultimate solution came from an unexpected direction: dieselization. Multiple diesel units coupled in consists distributed tractive effort across several locomotives. A 3-unit diesel consists producing 6,000 combined horsepower, applied that power through 3 sets of couplers instead of 1. The peak force at any single coupling dropped proportionally. Slack action was smoother because multiple locomotives pulling in coordination took up slack more gradually than a single massive steam locomotive slamming 135,000 pounds into a standing train. By 1950, as diesels displaced big boys, coupler failure rates dropped dramatically. Not because diesel locomotives were weaker, they weren't, but because distributed power changed the physics. The force that broke couplers when concentrated at one point became manageable when spread across multiple locomotives. Oh, the men who died in coupler failures between 1942 and 1950 were casualties of a transition period. The engineering that created Big Boy, the drive for maximum power in a single locomotive, exceeded the infrastructure's capacity to handle that power safely. And the couplers designed in the 1880s and upgraded in the 1920s weren't built for 135,000-pound tractive efforts. Neither were the operating procedures. Neither were the trains. Big Boy demonstrated that bigger wasn't always better. That power without control created danger. While that infrastructure, including the supposedly simple matter of coupling freight cars together, imposed real limits on locomotive capability. Exceed those limits and people died. Not metaphorically, actually. Crushed between cars when couplers failed. It killed in derailments when trains separated on grades. Injured by slack action that grew more violent as locomotive power increased. The railroad industry eventually solved the coupler problem. Modern freight couplers are rated for 350,000 pounds and up. High-strength steel, improved metallurgy, better design. Yeah, these couplers can handle the forces from even the most powerful modern locomotives, but they came too late for the Big Boy era, and too late for the men who died when American horsepower overpowered American infrastructure.